Okay, so in this section we're going to come up with a differential equation that models the position of an oscillating spring. So it means a spring going up and down. So here's the idea. So say we have a spring here. So right now the spring is not stretched. So it's in the equilibrium position, so it's not stretched. I could now take it and stretch it a bit. And the stretch past the equilibrium I'm calling S, say. When I stretch it, it's going to want to go back to the equilibrium position. So it's going to exert a restoring force that's in the opposite direction to where I'm stretching it. So the restoring force will want to bring it back to the equilibrium position. Okay, so let's look at now. Hooke's law states that a stretched spring exerts a restoring force F that is proportional to the amount of elongation or the stretch S past equilibrium. Mathematically stated, would say that F equals negative Ks, where here K is positive and K is called the spring constant. So you might say, well, why do we have a minus sign in front here? Well, the minus sign in front of the K denotes that the restoring force is opposite to the direction the spring is stretched. So if we think of the spring as being stretched downward, so say it was like this, downwards, stretching it downward, then we'd be viewing actually up as negative and down as positive, so things would be switched around. And in all the questions we'll be doing, we'll be viewing the spring as being stretched downward, so up will be negative and down will be positive. Okay, so I'm out of space here, so let me erase a few things and we'll keep going. Okay, so now here's my, say, unstretched spring here, and here's my stretched spring. So say I attach some mass to it at the end here, so it stretches it down, and it stretches it, say, S past the equilibrium position. So the weight of the mass here would be m times g. That would be the weight of this guy. That would have to balance the restoring force, so it has to equal k times s. So say this is in equilibrium right now. Now say we pull the mass down a bit and let it go. So if I pull this down a bit and let it go, it's going to oscillate, go up and down here. So let me write that here. Okay, so again, we're supposing that it's now past, it's pull x0 past s and let go. We then oscillate. So here it's at s, so say you pull it x0 past s here, so say it's down here times 0, then let it go, it's going to start going up, and then it's going to come back down again and oscillate like this up and down. Okay, so we're going to let x of t be the position of the mass at time t. Okay, so next thing. So next thing, by Newton's second law, then the sum of all the forces should equal mass times acceleration here. Okay, and the acceleration is the second derivative of position. Let's write that down here. Okay, so again, the acceleration is the second derivative of position, and it's going to equal the sum of all the forces. So you're going to have the restoring force of the spring. I'm just writing x and rather than x of t, but it should be x of t there, and just writing it as x. So it's going to be x plus s would be the restoring force of the spring plus the weight of the mass, so mg. Okay, I can then, so that's all the forces on our system here. I can then multiply the minus k in here. So let's do that. And again, it's minus because the restoring force is upward, which we're calling negative. And the mg is downward, which we're calling positive. Okay, so multiplying this in, we get then, we'll get this then, negative kx minus ks plus mg. But up here, the mg equals ks, so actually these two will cancel, because again, this guy equals mg. So we can conclude then, so hence, So hence we'll have our, this will be our differential equation then. So it'll be our mass times the second derivative of position equals negative kx. Okay, let's divide both sides by m here. So doing that we get then. Okay, so we get this then. So I'm out of space here, so let me erase a few things and we'll keep going. Okay, so I've written our differential equation over here again. So this equation describes simple harmonic motion or free undampened motion. So here's how the oscillating spring would look like. It would go up, it would be down, and then go up and down all the way. So it looks like it's going to describe, looks like it may be a sine or cosine type thing. We're now going to solve this differential equation. But first I'm going to make a substitution. I'm going to let k over m equal omega squared or w squared. Let me write that here. Okay, so I'm letting my omega squared or w squared equal k over m. So plugging in up here, we'll have our second derivative then equals negative omega squared x. Moving this over here, we'll have this differential equation. I'm writing x double prime rather than this now to solve. We can now use theorem 8 to solve this. So by theorem 8 then we know the solutions will look like e to the mx for this guy here. Okay, so note then. Actually I messed up here, should have been t up here. T is the independent variable here. Okay, so that'd be x equals e to the mt. So the derivative then would be m e to the mt, and second derivative would be m squared e to the mt. Let's now plug into the differential equation up here. So doing that we get then. Okay, so plugging in place of x, putting e to the mt, in place of x double prime, putting m squared e to the mt. I've done that here. Factoring out the e to the mt. E to the mt is in 0, so we can drop it off here. It means the m squared plus omega squared is 0. I can then solve for m, so subtract w squared on both sides are omega squared, and then take square root. So doing that we get then. Okay, so subtracting w squared on both sides, and then taking square root will be a plus or minus. I'll be square root of minus w squared, which will be then plus or minus omega I. We can write that as 0 plus or minus omega I, or let's call it w, I guess, wi. Okay, so we need to recall then theorem 5 when we have a complex number like this. Let's recall. So recall then in theorem 5 when you have a complex number, so say our m equals a plus bi, then a general solution will be, well in theorem 5 it said y, but here we're using x as the dependent variable, and t is the independent variable. There's going to be e to the at, then c1 times cosine of bt plus c2 sine of bt. So in our case, the a is 0, and the b would be our w. So plugging those in, I'm out of space here, but plugging those in then, so let me erase a few things and we'll keep going. Okay, so again we have our solution looks like this when our m equals a plus or minus bi. In our case our a is 0 and our b is w, so it's going to be this then. And e to the 0 is 1, so this will just disappear. So let's take that away. So this is the solution then of our differential equation. So, and that differential equation was modeling the spring oscillating up and down. Okay, we're going to simplify this a bit more here. So let's make a substitution. Okay, so we're going to let big A, we're going to actually call it amplitude later, equal the square root of c1 squared plus c2 squared. So these coefficients in front of the sine and cosines here. Then I'm going to divide the differential equation by our a, which I've done here. And then note here, if I square this and add to this, it's going to equal 1. So let me just show that here. So note here, if I take the c1 over a and square it, and plus the c2 over a and square it, so squaring this one will be c1 squared over a squared. This will be c2 squared over a squared. So the whole thing will become c1 squared plus c2 squared over a squared. But a squared is defined to be the square root of c1 squared plus c2 squared. So when I square, the square root will go away. So it'll be just c1 squared plus c2 squared over c1 squared plus c2 squared, which is 1. Okay, so therefore, these two you can think of as points on a unit circle, because r equals 1 here. So you can think of this one as cosine of some angle and this one as sine of some angle. So let's write that here. So it follows then that c over a equals cosine of b and c1 over a, sorry, and c2 over a equals sine b for some angle between 0 and 2 pi. Again, because up here we've shown that these two are points on a unit circle, and the points on a unit circle can be described using sines and cosines. Okay, next thing, let's recall a trig identity. So recall that the sine of a plus b equals cosine of b times sine of a plus sine of b from times cosine of a. So trig identity. Okay, let's make a substitution now. Let's let a equal the omega or wt here. Actually, I just noted something. I want to have these switched around here. I can do that, it's fine. The angle will change, is fine. But I can think of this as sine of b here, and this is cosine of b. I'll explain why now in a second here when I write it out over here. Okay, so this would be then cosine of b sine of a, but a now is omega t, so it'll be sine omega t plus then, so plus sine of b cosine of omega t. But now the cosine of b is the c2 over a, which we'll write in a second, and the sine of b is c1 over a. So making those substitutions here, we'll get then. Okay, so making the substitutions, I switch these both around, so I'm going to put this one first. So it'll be sine of b, which is c1 over a, cosine of omega t, which I have here, and cosine of b, which is c2 over a times sine of omega t. Now let's multiply both sides by a. So doing that, we get then. Okay, so multiplying both sides by a, then we'll have c1 cosine of omega t, c2 sine omega t, which is our x of t. So we'll have then our x of t equals a sine omega t plus b. Okay, so this is the solution then to our differential equation, which was the solution to, for the simple harmonic motion. Okay, so I'll be using this in this section. Actually, just this part here. Okay, so let's leave the video here then. And the next video we'll do an example using this. Okay.